So let's talk about the hidden logic that pretty much runs our entire world. We're going to pull back the curtain on the invisible rules that make everything from your phone to a massive factory work. And maybe more importantly, why sometimes they just don't. I mean, have you ever really thought about this? Why do systems that seem totally perfect on paper with all the best parts suddenly just fail? You do everything right, you follow the schematic, you use top of the line components, but the whole thing just refuses to work. It's maddening.
And that brings us to the heart of the mystery. There's this great line from one of our sources. A circuit can be electrically correct and still fail as a system. Whoa! So if it's not the individual parts, what on earth is it? Well, the answer is in the invisible logic, the ghost in the machine that ties everything together. Yeah, it's all about digging into a system's hidden rules. To really get why things go wrong, we have to look way beyond a simple shopping list of parts and start thinking about how those parts dance with each other over time.
Think about it. Long before anyone writes a single line of code or draws a circuit, the real designers have to answer these huge questions. In what order do things need to happen? What has to happen at the exact same time? And what does the whole shebang look like from the moment you turn it on to the moment you turn it off? Get these wrong, and you're doomed from the start. And this leads us to a really, really critical idea that engineers basically live by: the difference between a system's structure and its behavior. It's what it is versus what it does.
So you can think of structure like taking a quick snapshot, a single photo. It's a static look at the components. It's all about voltages and currents, asking, okay, if I put this input in, what single output do I get right now? But behavior? That's the whole movie. It's dynamic. It's all about what happens over time, what happens first, what happens next, what's happening in parallel. This is where the real magic or the real disaster happens. So when we talk about what happens when, it really boils down to two basic ways of doing things: sequential and parallel. It's the difference between taking things one step at a time or, doing a bunch of stuff all at once.
Okay, first up, let's talk sequential. The perfect way to think about this is baking a cake. You absolutely have to mix your flour and sugar before you add the eggs, right? Every single step has to be finished in order before the next one can even start. It's logical, it's predictable, and it's pretty straightforward. You see this all the time in the real world. A digital voltmeter is a perfect example. It has to follow this super strict order. Pick a channel, then sample the signal, then convert it, then process it, and only then, at the very end, can it display the result. You just can't show a result before you've even taken a sample. Here, order is absolutely everything. But what happens when you need speed? What if you need to be responsive? Well, that's where the parallel process shines. Just picture a crazy busy restaurant kitchen. You don't have one chef doing everything one step at a time. No way. You've got multiple chefs working in parallel. One's chopping veggies, another's searing a steak, a third one's plating dessert, all at the same time to get that food out fast. Okay, so let's break down the trade-offs here. Sequential is way simpler to design, but it's slower, and it has this huge vulnerability, a single point of failure. If one step in the chain breaks, the whole thing just grinds to a halt. Parallel, on the other hand, is way faster and more resilient, but man, is it a lot more complex to get right. All right, so we've got these two big ideas, sequential and parallel. Now for the fun part. Let's see how they actually play out in the real world, from these giant, sprawling factories all the way down to the tiny little chips inside our phones. Back in the day, manufacturing was a classic example of this over-the-wall design. It was totally sequential. The engineers would design something and then just metaphorically toss the plans over the wall to the manufacturing team. Any problems? They weren't found until it was already on the production line, which was slow and super expensive. The modern way? It's concurrent engineering, a parallel process. Design and manufacturing happen together from day one with constant simultaneous feedback. And that kind of parallel thinking, that's the magic behind what we call CAD/CAM, which is computer-aided design and manufacturing. It lets us turn a digital blueprint directly into a super precise physical thing, just like what this CNC machine is doing right now. The result is a process that's just faster, more accurate, and way higher quality. And what's so cool is that this same exact idea of parallel processing, it scales all the way down. I mean, right down into the heart of all our modern tech, you'll find the CPU, which is an absolute master of doing tons of things all at once. So when you hear people talk about a CPU, you always hear about this power trio: clock speed, That's just how fast it does one single thing. But we kind of hit a wall there. We couldn't just make them infinitely faster. The big breakthrough was adding more cores. The number of cores tells you how many separate jobs a CPU can tackle in parallel. Ever wonder how your computer can stream music, let you browse the web, and run an antivirus scan all at the same time without melting? Yep, that's your multiple cores working in parallel. So here's the kicker. It's not actually a battle of sequential versus parallel. The smartest, most robust systems out there have figured out how to get the best of both worlds. The truth is, pretty much every complex system you use every day is a hybrid. It cleverly mixes and matches sequential and parallel processes to do its job as effectively and reliably as possible. Let's take a smart energy meter, for instance. Perfect example. When you first power it on, its startup is super strict and totally sequential. It has to initialize its parts, then it has to calibrate itself. Order is crucial. But once it's up and running, it's a parallel powerhouse. It's measuring your energy use, talking to the grid, logging data, and updating the little screen, all at the same time. Because at that point, speed is what really matters.
And all of this boils down to one beautiful, simple design principle. It's the golden rule for building anything that works. Use sequential logic where order matters, and parallel logic where speed matters. It's that simple and that powerful.
So, I want to leave you with a thought. Now that this hidden logic is a little less hidden, start looking for it. Where else in your world do you see this elegant dance between that strict step-by-step order and the incredible power of doing things all at once? The more you look, the more you'll see it. Absolutely everywhere.